It's 2:30, welcome back. I'm Michael Johnson and I'm sharing this session. We have an unusual session because it's 2 speakers and then coffee, so you can have it fresh for the third speaker before the poster session. So the first of the 2 speakers before coffee is Dorette Pronk, and Dorette is going to be talking to us about double fibrations.
Thank you, Mike, and also thanks to the organizers for it. This is loud. Let me play this. Thanks to the organizers for a wonderful conference, and really such a great place to be together and meet new people. So many new people, that's also great. And thanks to the organizer committee, the scientific committee, for inviting me to speak. And it's not my fault. I really don't want to hear myself. Good. Well, in the meantime, let me just say that this is joint work with Jeff Rodwell, Michael Lambert, and Martin Shield. And the very last slide is starting new work with David Myers. And let's get started here. So I want to talk about double fibrations. So I will not say much about double categories because this has been the conference where I have heard most about double categories except for the workshop in November that was organized at Rice. But my double categories are pseudo today. So besides just having our diagram here that you would expect as an internal category in CAT, we do ask that there be associativity 2 cells, invertible associativity cells, and left and right emitters. So they are allowed to be there. So we're looking at pseudo category objects, and I'm putting them in an arbitrary 2 category right now because I will have also the category of fibrations later on to look at. So this is the definition. And so double category is then a pseudo category in Kant. And just for notation, we have the weaker arrows which are composing just weakly as in the bicategory, and we have the tighter arrows. And so the guys that are tighter where the composition is strict, which are coming from the category C0 and C1. So the arrows in C0 are going to be called arrows. And the other guys, the objects of C1, are going to be called pro-arrows in this talk. And they will generally be drawn horizontally, but I do not want to make that kind of horizontal arrow, vertical arrow thing, because it's forever confusing. And then we have double cells, which then have the vertical domain and codomain to be pro-arrows, and the horizontal domain and codomain to be arrows. If we take a double category where the C0 category is just one object category with only an identity, then we end up with a monoidal category. And so this is a useful way for many to study monoidal categories in the context of double categories. Double categories also generalize 2 categories in various ways. The one that I will use today is via the quintet construction, already introduced by Erisman, and so where we have those classes of arrows, that's the arrows of the original 2 category, and the double cells are 2 cells. What we often do is that there's actually a subclass of our arrows, especially if it's a bicategory, that we would like to isolate from the other ones. And so if you have a subclass of arrows that's closed on the composition and has identities, we can put those in the vertical direction and we keep the horizontal direction more general. This is an important way to construct double categories, and they help to study that other class while we still know about the tighter arrows that are sitting inside our 2 category. And so some standard examples are where we have sets as objects, functions as arrows, and relations as pro-arrows. We have also prof with categories as arrows, functors as, categories as objects, functors as arrows, pro-functors as pro-arrows, and spans where we have the arrows of the category as our arrows of the double category, and spans in A as our row arrows. These will come back. Okay, now double cat is unfortunately not a double category itself. It would be very convenient if it was, but it isn't. So I will see it today as a two category, where we have the double categories as objects. We will have in a moment our double functors, and then the transformations I'm taking between the functors are going to be the ones that have as components the arrows, so the tighter direction of the double category. So what are double functors? Even though you probably know, I want to talk about them for a second and point out something. So we are of course looking for a pair of functors, F0 and F1. And what I want you to notice here is that because we're looking at pseudo functors, we have an invertible cell here. So composition is only preserved up to a 2 cell. So the same thing is true for identities, but contrary to what you would do if you were doing simplicial objects, in the category case, we want this to be strict. So source and target are preserved strictly. And that's going to play a role in a sec. So I just want to point that out. Okay, so we want to define double fibrations today. And since you guys have all been listening to all these lovely talks about the Groton deconstruction or category elements, I tell my students not to use Groton deconstruction, and then I do it myself. Anyway, the category elements. When I started this project, I wanted to start with okay, what are my indexing functors? And then we're like, what are our indexing functors? Because double cat is not a double category. And so we'll start on the other end, and then finally find out what the indexing functors should be. And so what I don't know is what the double fibration is, but I do know what internal category objects are. So, and I know what fibrations are, so let's start there. And my goal, by the way, in the process is to generalize all the known notions. Well, all, these 4 at least. So David Myers had given us a lovely double Groton deconstruction, and when I saw that I was like, okay, where does that fit? And so I wanted to figure out what that was. In the meantime, Michael Lambert had already looked at discrete double fibrations and was really inspired by Bob, because Bob had already given us a Groton deconstruction, so our category elements. Then there's the monoidal fibrations introduced by Christina and Joe, and 2 fibrations which have been around for quite a bit longer already, introduced by actually Igor Bakovic first, and then further I worked out very luckily. And so we wanted to have something that would put all of this together. Double categories have a tendency to do that for you. So. Okay, and in all of these cases we have an indexing functor and we have an elements construction, so our next hope is that we will also be able to do that. Okay, so rather than starting with the indexing, what we're going to do is I'm going to look at internal categories in fibrations. What do we get there? And in order to get the right definition, I'll quickly review arrow categories for you. And so if I have a 2 category, I can make a 2 category of arrows, where the objects are the arrows. For the arrows of the arrow category, we need to take some kind of squares. If we take a pseudo arrow category, then the squares are commuting up to a 2 cell, so this is a square with an invertible 2 cell in it. And then the 2 cells become these commuting cylinders. If we have the strict version, then I just ask what the squares commute. And so now I want to note again for a moment, what do we know about internal functors compared to those squares? And the point is then that we can get internal functors as internal categories in the square category, except I need to be careful that the source and target are going to be in the strict squares, where the rest can be pseudo squares. Okay, keep that. And of course, if I restrict myself to the strict functors, then everything lives in strict squares. Okay, now fibrations, probably don't have to say much here. We have these lovely lifts with special properties. What I want to say is that if you make a choice of lifts, you have a cloven fibration, so that's a cleavage. So, and today all my fibrations will have a chosen cleavage. So every fibration just shows up as many times as it needs to with its different cleavages. And cloven fibrations then correspond nicely to index categories from so contravariant functors into cats. So yesterday you saw them into sets, today they come to cat. And the growth and deconstruction of category of elements gives you that correspondence. So what should then be a morphism between fibrations? You have two choices, because my fibrations are cloven. And one is that we just require that the Cartesian arrows be preserved. I'm not asking for cleavages to be preserved here. And the second one is that, the more strict one, is that cleavages will be preserved. And so I will use CFib for the category with cleavage preserving arrows and fib for the more general one. But notice that all squares have to now live in strict, because maps between fibrations, I didn't have a 2 cell in that square. Oh wait, one little thing here that I want to say. So we had fib with index categories. CFib, if you go for the cleavage preserving arrows, then the transformations change. So here we have pseudo transformations, and the second one we get the strict natural transformation, so be aware of that. Okay, so what is then a double fibration? The first idea which we just stole from Michael, well, Michael was part of the group, so we could do that, was to say, well, we just take a pseudo category in fib. That worked for the discrete ones. But then we get a completely strict diagram, and there's a little problem, because, so I asked that P not be a fibration, P1 is a fibration, and this guy needs to be a fibration. And if you have played with fibrations, you know that that is not a given normally. So in order for this guy to be guaranteed to be a fibration with the first stack through, I am going to have to do what we kind of knew already to do. That was the source and target need to be treated specially. So I've just said that, so we can actually go to the next slide. And so what I'm going to ask for is that source and target have to preserve cleavages, and the rest only has to be Cartesian morphism preserving. If I do that, then the fallback is going to be a fibration. And so basically, wait, I should stop there for a little longer. So this is our notion of double fibration. So I wanted to give you those slides to kind of help you see how did we get there. Why is this the right notion? Or at least why is this a notion worth considering? The right notion, not sure. This is at least one that is useful. So notice everything is strict, which might be surprising you at first. And we have an extra condition on source and target. Okay, some examples. So this is one way to see that we didn't do anything too crazy. If we take E0 and B0 both B1, then we recover monoidal fibrations. If we look at two functors, the two functors are two fibrations precisely when the quintet construction gives me 1 of ours. When P0 and P1 are discrete fibrations, we end up with Michael's original description, and David Meyers' work fits. So, good start. And a couple of other examples that are useful, in, especially in computer science, are the domain fibration. If you take the image morphism from span to rel, we get a double fibration. We have a codomain fibration provided that B1 and B0 have finite limits and are preserved by source and target. So, and there's a fan fibration, there's a couple of other useful ones that I've worked with in other places. Okay, now some of you guys might be thinking, well, but double categories are internal categories, and didn't we have another way of doing this using street construction? And that's why I don't want to say this is the right notion, because with the street construction you can get a couple of other ones. But ours are the right ones if we assume up front that we have a strict double functor. Then it is precisely an internal fibration out of street in double cat with pseudo functors and pseudo transformations and so on. If and only if it's one of ours. If you allow yourself to become pseudo, then there are some other options which I don't want to go into today. We got paper. It's on the it's in tag and on the archive. Okay, so then my goal for today is to look more carefully at the elements construction, because we have generalized everything, and but we want to know what can we do with elements, and what about fibrations. So how do I get the correct indexing? Well, what you need to remember there is that categories are monoids in span. So, and here's the star for that. So, that correspondence might be used by Joe and Christina to show that I can lift the fibrations with index categories to pseudo-monoids in fibrations and pseudo-monoids in index categories. And we want to do the same thing, but we have to go a level higher. And so we will be working with double two categories. So internal categories in two categories. And that means that we get a double category with between any two double cells, potentially three-dimensional cells, so to say. And so now I see that in any two categories, pseudo-categories in K will correspond to pseudo-monoids in the double two category of span K. And the span, so the triple cells there are just going to be triples of two cells that are making the two cylinders commute. And then we can also restrict ourselves a little bit if we don't like all spans. We will actually sometimes look at spans that are sitting in a particular subclass of the arrows, we call it span sigma. Okay. So then it turns out that our preferred codomain for the indexing functor, at least for right now, is span cat. So that means I have categories, I have functors in the vertical direction, or functors as arrows, and spans as throw arrows, and two cells and triple cells between them. And if we do that, then we find indeed an equivalence of categories between double fib and I span cat. Now, how does that work? We can actually borrow everybody's proofs and just get a new proof that way. And so we first say, well, we fib an ICAT restrict to CFib with ICAT with the strict transformations. So I can take spans and I get span CFib and span T ICAT will be corresponding now. And then we can lift that a la Joe and Christine's construction, and we get double fib and I span cat.
What is about pseudo? Is it the type or?
No, thank you for asking. What is a large pseudo functor? That's a very good question. I forgot to read my own slide, that's what happened. So what we have here is, the pseudo part has to do with the functors that we actually have, because they are pseudo, but the whole diagram around the functors, we're now asking only for transformations in one direction. So they're not, so the structure transformations are only one direction. They don't have to be vertical. So that's where that comes.
Is that the same thing as a pseudo-monad in span?
Yes.
Yeah.
Thank you. That's the right answer. Okay. So I could actually defined the whole thing, we proved the whole thing without using the elements construction, and I was super disappointed. I was like, come on, wait a second, I need that elements construction, I want to understand it better. And so, but the good thing is we can just trace the elements construction down, and it's actually really, but I don't have to do that for you, I can show you directly how to get out of it. And so, just to remind you, this is what span cat looks like. Maybe I should have put that there earlier. But what we get now, if we have an F from a double category into span cat, and by the way, there's a bunch of ops missing after here, so put them in where you want them. And we first get F naught is landing in span cat 0, which is cat. So here we just have a functor into cat. This F1 ends up with the spans and the maps between the spans, but I can restrict myself to the apex, and I have again a cat. Great. There we have an elements construction, so let's apply them. And it turns out that's exactly what you need. So elements F0 is precisely the elements construction of F0, and elements F1 is just the elements applied to apex after F1. Now, of course, there's a bit of work to be done to get the structure errors, which I'm not going to tell you today, but they are in the paper. I'd better tell you about what I can do with this. So, this was very nice, and we had barely published this, and Evan Patterson took it. I'm so happy that he did that, and showed us that now we can do decorated co-spans as an elements construction, and they're slightly more general than the original version, because we can now also decorate the feet of the spans, not just the span itself. And David just made me aware of a paper where this could be used. I haven't had enough time to completely work it out. And David's paper is also reviewed as the elements construction after. So his indexing functor was going into prof, but prof sits nicely within span cat. And if you take the composite and take our elements, then we get David's double graphic. I had another goal when I started this paper. And my question at the beginning of lockdowns was, so the elements construction gives me fibration, but it also gives me an optics co-limit. How are those two things related in other contexts? And so, by the way, I was really grateful for the talk yesterday for all the other cool things that the elements construction can do. So we have questions left, but I wanted to know about the optics co-limit, and I was like, span cat is not good because it doesn't have double categories as objects. So how am I going to ever get my co-limit here? And so here we have another really good thing, and that is that some of you guys might know mapping into span set can be viewed also as mapping into prof. You need to do a little bit of work, because you need to remember that if you have something lax going into spline, that in case of sets going into, then you get the prof functor. In our case, if you take a lax functor from one object double category into span cat, you actually get a double category. Because the lax stuff gives you the extra arrow to create your category of objects, category of arrows, sorry, category of objects. So, lax double pseudo-functors correspond into span cat corresponds to normal lax double pseudo-functors into prof double cat. So we take internal pro-functors in cat horizontally and internal categories in cat as the objects, and they become double categories. And we've just started working on this, but right now, besides looking at all the details, it looks like we do get the optics double co-limits in the strict direction here with the elements construction. That's, I think, what I want to tell you today. So, okay, here we go, and thank you.
Thank you, Dorette. So time for just a couple of questions. Yes?
So you mentioned your growth deconstruction provides an equivalence of categories, but in Lambert's paper he constructs an equivalence of virtual double categories. So does your theorem also extend to this?
And we have to still look into that. I tried to push back our authors there, but they were like, let's publish this and we'll work on that later. Actually, that is one thing that I am curious about. So I probably look for some co-authors to help me do this. Because
I think that's what you did a second.
Oh, thank you for your talk. I was just interested in the double two categories. That was categories internal to two categories. Like, what happens if you do categories internal to monoidal categories? Are they like a one monoidal version of Christina's monoidal two categories?
well, not really. Let's see. So if you do category objects in, you said monoidal.
In monoidal categories. So you did it in two categories. So
Yes.
a special case would be in.
Yes, and so you have your, let's see, so you get monoidal structure on your objects, your arrows, so that is, I think they do commute, yeah, but I probably need to write it down for a moment.
Okay, yeah, question.
Dorette, do you have some kind of microcosm principle that did you prove that double vibrations are the double vibration over double categories? So you know, Hermida proved that all two vibrations is a two vibration over the category of categories. So that is kind of a theory. So fib
You want to-
fib over cat is a two vibration.
Correct.
Is double fib over double cat a double vibration?
Well, it can't be, because double cat is not a double category, that's the issue. And so you would have to go, you probably have to go for that prof thing that I just created, the prof double cat. And that's why you would have to try to do it, and I haven't done that yet.
Are you absolutely sure that double category is not double category?
Yes, it's enriched over double categories, but it's not double category itself.
Two more questions in the queue, and I think they have to be quick. Adrian?
So I had a question, just you had your embedding of prof into spans of cat, but that's sort of leave lax, right? Because
Yeah, but that's okay, because we weren't allowed to be lax.
Okay.
But I probably didn't find it correctly. Someone needs to fix my slides for me.
Thank you very much for the talk. I was interested in knowing, so you mentioned that in the case of internal fibration in the sense of suite, it corresponds to the definition you suggest for strict functors, strict double functors. And I was wondering whether, if you consider the subcategory of the two categories of quickly internal categories in CAT, and if you compute or if you expand the definition of what is a fibration in these two categories, would that be the same as the original definition in the case where you consider pseudo functors?
Yes, so there's three other results that I didn't put on my slides. I obviously should have left them on there. Can I just talk to you afterwards? I will, because I just need to look them up quickly. I don't want to go the wrong way now. But it's every time it's like you have one, but you need to do something special with source and target, and I just need to make sure I say it right.
That's best because we need time for people to change rooms if they do. So let's take